We're going to begin our study of rules for finding derivatives of functions. So we'll learn to calculate derivatives on our own and not rely on the calculator anymore. In many cases, we will be more accurate because the calculator is doing an approximation. It actually is finding slopes over very small intervals. We will be using some analytical rules. So we'll be incorporating the things that you noticed in your lab yesterday, but thinking of looking at rules for particular classes of functions. Today, we're going to look at derivatives of power functions and polynomials. Remember that power functions look like this, x to the a or x to the k. They may have a coefficient, so they can be p x to the a, but notice the position of x in the base, and the power is a numerical power. Polynomial functions, remember, are just sums or differences of power functions, so they can be a p x to the a plus an a x to the b plus a c x to the d, and so on. There's a couple of what we could call power functions that we already know the derivative of. For example, we know the derivative of a constant function. So the derivative of the line y equals 3 or y equals 4 or y equals 5. So the derivative of just some constant function is 0 because its slope is 0. We also know the derivative of a linear function, so derivative of, we can call the linear function mx plus b, and that derivative is just the slope of that linear function. But we're going to expand our analytical knowledge of how to find function rules. Before we do that, just a reminder of some laws of exponents. Remember, for multiplying, we add exponents. The bases have to be the same. If we have an exponent raised to a power, so a power to a power, we multiply the exponents. The last two are probably more critical because neither of these really looks like power functions to begin with. But remember the radical, that if I have some root of x to some power, then I can rewrite that as a power function. It's power over root. So you can see where the p and the r go. They are, it's alphabetical, so it's always power over root. And then remember that a negative exponent is equivalent to having a fraction, to dividing by that term. In your lab, you've already seen some of the rules for power functions. You saw that the derivative of x squared was 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is x cubed. Remember this notation, this d dx, we talked about in the last chapter. It's kind of the command version. I'm finding the derivative of the function that follows, and so I'm reading that as the derivative with respect to x. That's what that dx means, of x squared is 2x. So if we notice a pattern there, we would say that in order to find the derivative of a power function, we bring the power down and subtract 1 off the power. So here's my kind of new rule that's more generalized for power functions. So if I applied that rule, say, for the derivative of x to the fifth, I would say, oh, well, I bring the power down, subtract 1 off the power. That leaves me with 5x to the fourth as the derivative. Okay, let's do a few examples, making sure that we understand that rule. So we just did this one. If y equals x to the fifth, then let's talk a little bit about notation here because the function is presented in y equals form. In order to describe its derivative, I'm going to write y prime equals, and then the formula for the derivative, 5x to the fourth power. If I wanted y equals m to the 2/3, then its derivative, bring the power down, subtract 1 off the power. 2/3 minus 1 or minus 3/3 is negative 1/3. You do get a little workout with fractions with these power functions. Number 3 is a good example of a power function that's kind of in hiding. It's written not as a power function, but I'm going to remember my laws of exponents. I would see this as the square root of x to the fifth, even though the 2 is not written out there. Kind of have an understood 2 here. And so then when I go to change it to a power function so I can find its derivative, I'm going to rewrite it as power over root. Notice that that is not y prime yet. All I've done is rewrite the original function y in a different format. Then in order to find its derivative, I have to bring the power down, subtract 1 off the power. So 5/2 minus 2/2 would leave me with 3/2. And typically, I'm just going to leave it in that form. That's 3/2, not 3z. So 3 halves. And I'm just going to leave it in that exponential form rather than changing it back to the radical. Number 4 is another good example of something that doesn't appear as a power function but actually is. So 1 over x cubed is the same as x to the negative 3 power. I'm going to rewrite it first. Notice that's not the derivative. I just have equal signs there. It's the same as the original function. Then now that I have it in this, it looks like a power function, I'm going to apply that rule and actually find the derivative. Y prime is bring the power down, subtract 1. Be careful, negative 3 subtract 1 is negative 4, not negative 2. So just make sure that you're paying attention to some common mistakes that you might make there by subtracting. Couple more rules that will allow us to do some more interesting problems. Thinking of a constant times a function, the derivative of a constant times a function. If I think about what multiplying a constant times the function does, it increases the y values by multiplying by that constant. So then if I think, well, what would that do to the slopes or the derivative? The derivative or the slopes would be multiplied by that same constant. And so if I have a coefficient times a function, I'm just going to bring the coefficient along and find the derivative of a function. So in other words, the derivative of a constant times a function is just the constant times the derivative of a function. Another rule that's helpful is thinking about what if we add or subtract functions. It's the same situation. We can do it with addition or subtraction. You can get that there. That if I were adding or subtracting two functions, it would affect the y values in a like manner. So that's just going to be the sum or difference of the two functions, the derivatives taken separately. Okay, we're going to work a little bit on finding the derivatives of some power and polynomial functions, looking at multiple power functions kind of added or subtracted from one another. So in the first example, I see I have a series of power functions, each of them with a coefficient. So I'm going to be employing all the rules I've learned so far. So I'm going to write it out long, and then eventually we'll get to the point where we won't need to write as much. But since this is our first example, I'm going to write each of the steps. So I'm going to go directly to finding y prime. The 4 is a coefficient, so I'm just considering the term 4x cubed because I know each time I see an addition or subtraction, I can just treat them as separate problems. So the 4 is a coefficient. The 4 is going to come along. Then I need the derivative of x cubed. The derivative of x cubed is 3x squared. Then I have minus. The 6 is going to come along. The derivative of x to the 4th is 4x cubed. Plus 2x squared, the 2 is a coefficient. It just comes along. The derivative of x squared is 2x. Then I get to the minus 4. Well, that 4 is not a coefficient on any function. There's no function after it. It's just a constant. And I know that the derivative of a constant is 0. The other way to think about that is that if I considered all the 4x cubed minus 6x to the 4th plus 2x squared as a function itself, the minus 4 would make a translation of that function. It would shift it down, the y values down 4 units, and would have no effect on the slopes of the graph at all. It would only change the horizontal position of the graphs. So the derivative of that 4 is 0. Then I would want to simplify my result a little bit. I'm going to go ahead and multiply 4 times 3 and get 12x squared minus 6 times 4 is 24x cubed plus 2 times 2 is 4x. Notice that I could have shortcut that process. I know the 4 is going to come along. I'm bringing the 3 down. 4 times 3 is 12. Subtract 1 off the power, x squared. 6 times 4 is 24. Subtract 1 off the power, x cubed. 2 times 2 is 4. Subtract 1 off the power, x, and the derivative of the 4 is 0. The next function has a little bit of a challenge in that it is not written as a power function. So I'm going to rewrite. I see two pieces there. They separated the subtraction sign, so two functions subtracted. I'm going to treat them as two little separate functions. So I'm going to rewrite it first, and then I'll find the derivative. So the first function is written as a radical. I would like it to be written as a power function. So I'm going to rewrite it as power over root 4 thirds there. The next one presents a different challenge. I see that I have a power function in the denominator, but I also have a coefficient there. And I'm going to learn to see this coefficient as 1/2. So I'm going to leave the kind of numerical bits where they are and leave that coefficient as 1/2. I'm not going to rewrite it. I'm not going to move it. I'm just going to leave it as 1/2. So minus 1/2. Then I am going to rewrite that x squared as x to the -2 as a power function. Now I'm ready to find my derivative. So I'm going to label it as y prime. Bring the power down, 4/3. Subtract 1 off the power, 4/3 subtract 3/3 is 1/3. Minus, bring the coefficient along, 1/2. Deal with x to the -2, bring the power down, subtract 1 off the power. Then I could simplify my result a little bit, just rewriting it. I can't do anything to the first term, so I'm going to leave it as 4/3 x to the 1/3. Then the next one, I can go ahead and multiply my -1/2 by my -2 and get +1, so plus. Then 1/2 times 2 is just 1, and I get plus x to the -3. And there's my derivative function. The next example is a test in determining what's a variable and what's a coefficient. So I have a polynomial there with 3 terms. So I'm going to have 3 little separate derivatives. So I'm going to go ahead and start that derivative. I'm going to look at it and think, okay, the first one looks okay, the second one looks okay. This third one, I just want to think of it as, remember we talked about in the previous example, I'm going to think of that as 3/4 x to the third. So I'm going to pull out the numerical coefficient bit of it and then deal with the x to the third. So looking at the first term, 2 pi x cubed, I have to remember that 2 is a number, coefficient, it's going to come along. Pi is a coefficient, numerical coefficient, it's 3.14, it's going to come along. And then I'm just going to deal with the derivative of x cubed. So if I bring the power down, 3 times 2 would make 6. Pi comes along, x to the, subtract 1 off the power, 2. Plus, then I look at the next little example there, and I see 4, which I know is a numerical coefficient, and e. E is also a numerical coefficient. It's 2.7, blah, blah, blah. It's not an exponential function. It has no x in its exponent. It's just the number e. So I'm going to treat that, both the 4 and the e as coefficients. They're just going to come along. And multiply the 5 times the 4, and I would get 20. Then my e, x to the 5 minus 1 is 4. The last term there, 3/4 is going to come along. Bring the power down, subtract 1 off the power. I could simplify that last term to being 9/4 x squared. Remember, you're multiplying 3/4 times 3/1, which would give you 9/4. Then my last example here has a serious problem. It's a division problem, and I can't just put something out front like I was doing with the numerical coefficients, and I don't have a rule for dividing. In fact, we won't have a rule for dividing for a couple of days. And so we can't do this problem yet because we only have rules for when a function is added or subtracted. So we need to think, well, is there a way that I could rewrite that into a polynomial function, each term added or subtracted, and not actually be dividing? And I can do that. I'm going to rewrite the divided by x as x to the -1 times, and then what remains, that initial polynomial. So times x to the third minus 4x squared minus 2. I still can't do the problem because I still have multiplication there and I don't have a rule for multiplication. So I need to distribute that x. I need to actually multiply. So I'm remembering now when I multiply x to the -1 times x cubed, I'm going to add those exponents. So 3 plus -1 will give me x squared. I'm going to keep going. 4 comes. -1 times 2 gives me x to the first. Continuing on, distributing on, x to the negative 1 times 2 makes 2x to the negative 1. I still have not found the derivative after all that work. Notice the equal signs. Each of those functions is equal to the other. None of them is the derivative. They're just rewritten versions of the same function. But now I'm ready to find the derivative because I have everything added or subtracted. I just have coefficients in front, so I can find my derivative. Now y prime equals, bring the power down, subtract 1 off the power. Bring the power down. If I subtract 1 off this power, its power is 1. So that makes 4x to the 0. X to the 0 is just 1, so I get minus 4. Bring the power down, so plus 2. Subtract 1 off the power, x to the negative 2. Make sure you're subtracting off that power. So my final answer ends up to be 2x minus 4 plus 2x to the negative 2, or 2 over x squared. So let's just kind of look back through that one. What we noticed first was that we were dividing. We don't have a rule for division. So we rewrote the division as a multiplication by writing the thing I'm dividing by as x to the negative 1. Still can't do the problem because I also don't have a rule for multiplication, so I have to actually multiply. When I multiply, I add exponents. I'm distributing. I can distribute a single term into addition and subtraction. That's when I distribute. So adding exponents, negative 1 plus 3 gave me x squared. 4 is 4. Negative 1 plus 2 gives me x to the first. And then the last term didn't have anything, so it just becomes negative 2x to the negative 1. Then I began to find the derivative using my power function rule. Bring the power down, subtract 1 off the power. And that's how I found the derivative. Note that these are derivative functions, so they are describing the slope at any value on x. If I wanted to know the slope of a particular function when x is 0, I would have to find the derivative and then plug in the 0 for x to find the slope at that particular point. The slope is always, always, always numerical. What I found is a formula for the derivative that describes the slopes at each value of x. All right, that's it for today.